Let's have a look now at some worded examples for using this. And each time we need to consider carefully, are we going combinations or are we going permutations? So for a trip, you pack 3 pairs of shorts and 2 pairs of shoes. How many different outfits can you create? So this again is just the multiplication principle. I've got 3 pairs of shorts and 2 pairs of shoes. So it's a multiplication, 3 times 2, which gives me 6 possible outfits. So look at passwords. The password for the door to a building is chosen by selecting 4 numbers from 0 to 9, or 4 digits from 0 to 9, and no repeats are allowed. And it's always important that we consider if repeats are allowed or not, because that will change things a lot as well. But when they're typed in, they must be in the correct order. So for example, 1, 2, 3, 4 would be considered different to 4, 3, 2, 1. How many different possible codes are there? So we're saying here that the order matters. So it's going to be a permutations question. We're saying that the order in which I put the digits in is going to make a difference. So I'll basically be doing permutations. I've got, and be careful with this, there's 10 digits to choose from. There are 10 digits from 0 to 9, including 0 and 9. So 10p4, which is a big total of 5,040. A different door this time. The password for a different door is chosen by selecting 4 numbers from 0 to 9, no repeats, and 1 letter from X, Y, and Z. They can be typed in using any order, so it doesn't matter what order I put the digits in or the X, Y, and Z. How many different possible codes are there? So this time with the order not mattering, it's a combinations question. So the number of combinations for my numbers will be 10C4, and I need to choose a letter from X, Y, and Z, and I've got a further 3 choices, so I'll be multiplying by 3. So 10C4 for the digits, multiplied by the letter from X, Y, and Z, 3 more possibilities, giving me 630 in total. Let's now have a look at arrangements of letters in words. So if we take, for example, UWCSEA, I want to figure out how many unique arrangements there are for those letters. And don't worry, I'm not worried about whether they actually make a word or not, just the different arrangements I could get. So this is going to be permutations, because if the letters are in different orders, I want that to be counted as something separate. So it's permutations, and I'm basically choosing 6 from 6. There's 6 letters there, and I need to be positioning all 6 of them. So 6p6, which is 720. Let's now take the word school. So again, 6 different letters to choose from. So 6p6 is going to be important as well. But if I do that, I've actually counted some arrangements twice that I don't want to. And it's because of these these O's here. So these O's, if I do 6p6, I'm basically counting situations when they have been switched around, but that is not actually a different arrangement of those letters. Okay, so if this O here was switched to being there, and this O was switched to being there, well, that still is school. It's not made any difference. So for the 6p6, I actually need to then divide that by something to sort of discount those arrangements that I didn't actually want to be counting twice. So how many ways can the 2 O's be arranged amongst themselves? Well, there's 2 factorial ways that could happen. If I position this one here, that's 2 ways to position it here, and there's only 1 place left over. So if I do 6p6 and divide by 2 factorial, getting 360, that's the number of unique arrangements for school. And let's look at a longer word with more duplications, so the word possessions. So I've got 11 letters here, so I've got 11 letters to position, and I'm choosing from 11, so that's 11p11. But now I've got more divisions to make. I need to say that the 5 different S's, they could be arranged in 5 factorial different ways. And I also can see that there's another 2 O's, so there's 2 factorial ways that they could be arranged. So I do 11p11, divide it by 5 factorial and also by 2 factorial, and that then gives me 166,320 different combinations. And you can see now why these questions can be quite tricky, because you look at that number there, and if you'd forgotten to divide by this, it's such a big number that it's impossible for us to actually list out these combinations. So it's very hard to get a sense of whether your answer is correct or not. So you have to think very, very carefully about whether you've accidentally repeated counting things or not, and that can be quite hard to do. Let's have a look at another one. There's 6 seats at the front of the classroom. If 4 students come into a classroom and are told to sit in the front row, in how many ways can they be seated? So this is similar to one of the questions we said right at the start, which ended up being a permutations question. The arrangement of these students, the order in which they're sitting on that front row, is a fundamentally different arrangement. So this will be a permutations question, but this time around I'm not filling every seat. I'm only filling 4 of the seats. So it will be 6P4. I'm positioning 4 students in 6 places, and the order does matter to me, making it a permutations question. Onto this example here. 4 representatives are chosen at random from a teaching group consisting of 12 boys and 8 girls. Calculate the total number of ways that they can be chosen. So if I'm picking 4 representatives, I don't mind the order of those representatives, so this will be a combinations question, not a permutations question. And here, it's the total number of ways they can be chosen, regardless of gender, so I'm just choosing 4 from 20. I don't care of the boys and the girls' makeup, so 20C4, which is 4,845. If we take the same teaching group, but this time we want to have a look at the selections of 4 boys and 0 girls. So how many combinations are there for that? So still combinations, the order doesn't matter to me. But now, to get 4 boys and 0 girls, I'm basically doing 12C4. I'm choosing 4 boys from the 12 boys that I have, and 0 girls. Well, we could just ignore that because there's no combinations to account for there. If it's 0 girls, I've got no different arrangements for that. But we could say that that is 8C0, the number of ways of choosing 0 girls from 8. So 12C4, we could say multiplied by 8C0 gives me 495. What if it's 3 boys and 1 girl? Well, that means I've got to choose 3 boys from 12, so 12C3, and multiply it by 8C1. That gives me 1,760. Just one last example, 2 boys and 2 girls. So I'm going to choose 2 boys from the 12, so 12C2, and so multiply 2 girls from the 8, so 8C2, giving me 1,848. If we turn that into a probability question, what is the probability that the representatives will consist of 2 boys and 2 girls? So we've worked out how many ways there are of getting 2 boys and 2 girls, and it will be out of the total possible number of combinations of these 4 representatives, which is 1,848 over 4,845, which ultimately gives you 0.381 to 3 significant figures.